Hi and welcome to my channel. This is Rajdeep Rath. In this video, I'll be talking to you about a smart water monitoring system that I have designed for my apartment. It's an IoT project. It utilizes Arduino microcontroller and special non-contact liquid level sensors to gather liquid level information from PVC water tanks without actually making any contact with the water. The system gathers water level information through sensors. It is processed on Arduino and the output is dispatched through two different channels. On one end, it is sent to a simple analog 5mm LED based display unit, which is useful to the pump operator. And on the other side, it is sent to an online web server from where human readable messages are generated and dispatched to smartphones through the Telegram application. The stakeholders for this project are mainly the apartment dwellers who are interested in knowing the state of water level inside water tanks, and the pump operator who is responsible for operating the pump and ensuring there are no overflows or we don't run out of water on summer seasons. This system is a simple technological demonstration of two things. Firstly, you can see how non-contact liquid level sensors can be useful in the field of water monitoring, especially when you're dealing with drinking water supplies where you cannot afford contamination. And the second thing that we will be seeing is how we can leverage an existing API such as offered by Telegram application to easily connect our IoT device to smartphones without having to write a lot of code, without having to set up your own infrastructure. Going into this video, I'll be showing you the different components of the system, how they are laid out, how they interact with each other, and how the system works as a whole. We'll also be seeing how the sensors are actually installed on the water tanks, how the cabling is done, how the signal is received in Arduino, the different subcomponents of the Arduino setup, and how the signal is dispatched to the different channels. So that's all for the introduction. Now let's get started with the system. In this video, I'll be introducing you to a smart water monitoring system that has been designed by me for my apartment. This is an IoT project. It utilizes Arduino microcontroller and special non-contact liquid level sensors to monitor the water level inside opaque PVC water tanks without actually making any contact with the liquid. The system gathers statistics about the water level and dispatches it through two different channels. The first one is the analog channel, which is used to display the water level using simple 5mm LEDs. This is useful for a pump operator. And the other channel is the internet, so the notification is sent to the internet formatted in terms of human readable messages and dispatched through the Telegram API to different smartphones. The stakeholders in terms of this project are the apartment dwellers who have Telegram application installed on their smartphones, and they are all connected to the water monitoring channel on the Telegram app. This project is mainly a technological demonstration of what non-contact liquid level sensors can achieve and how useful they are in the domain of monitoring water levels for drinking water supplies. Through this video, I'll be introducing you to the different components of the system, how they are connected to each other, how they operate, and how the entire system works as a whole. I'll be showing you the sensor installation. I'll be introducing you to the sensors itself. We'll be taking a look at how the wiring is done, how the signal gets collected in Arduino, what sort of processing is done, what are the different subcomponents that are used along with the Arduino microcontroller, how the signal is dispatched through the analog line down to the indicators that have LEDs on it, and how the notification is sent to smartphones through Telegram API. So let's get excited and let's get started. So here now on my screen you can see a diagram representing how the system is set up. So I live in a 5-story apartment, and let's assume this is the 5-story apartment, and on the top of the apartment we have PVC based syntax tanks set up for containing the water supply of the building. And although in this diagram I'm showing you one syntax tank, we have around 6 syntax tanks, each of 2000 liters connected in serial. So that amounts to around 12,000 liters of water. And on the ground floor we have the security guard who operates the pump manually from time to time. They have a specific routine that they need to follow. So the security guard cannot actually peep into the syntax tanks to check the water level. So the problem that we had initially was there used to be overflow if the security guard was unattentive or not near the switch at the moment when the water reached a stop level. And the other situation would be in summers, we could not keep a tab on how much water is getting utilized. So eventually we would run out of water at midnight around, and that's quite inconvenient. So knowing this problem, I started thinking that what if I could design a solution using microcontrollers that could also help me learn a few things and maybe solve the problem that our people in the apartment were having. So after researching quite a few sensors online on Amazon, eBay, I found out that there are some standard sensors that are used to monitor water levels and perhaps automatically control the pump. But the additional problem I had was that our apartment has a specific requirement that nothing should be immersed into the water. So all of the sensors that I checked out online were all about inserting something into the PVC water tank, perhaps like 3 or 4 sensors immersed at different levels, and that could help the ready-to-use system judge the water level, and then it controls the pump. That's how it was. Mind you, in our case, there's another additional requirement, that is, pump cannot be operated automatically, and that is because a pump cannot run for a rather longer amount of time. It burns out. So they have a sequence of 1 hour, then some break, then again 1 hour, like that in the daytime, and only 1 hour in the evening. So after looking at this problem, and mind you, this place where it shows Arduino, this is where I stay. So just considering that this is a 5-story apartment, I stay in the 4th floor. So the first thing I did was I went to the terrace where the pumps are located, and I did a thorough investigation of the surrounding to understand how the water tanks were connected, which water tank was filled in first, and where the sensors could be attached, whatever sensor I decide to use. And then initially I had thought of using wireless system for communication between the sensors and microcontroller. But then I found out that eventually you might run into some problems, bugs, and it's a headache to repair them in such conditions. So for the first version of the system, going by a wired system would be the safest bet. So before I proceed to show you my custom version of the water monitoring system, I would like you to understand the need for designing a custom system in the first place. So when I head off to Amazon, you can see a few products randomly I have browsed here. So here you can see these products require sensors to be immersed into the water to be able to judge the water level properly. This is another kind of water level controller which requires you to insert this sensor into the water tank. And this is another one where you need to insert all of these on different levels. And this is, you can understand this, it's like for 25%, 50%, 75%, and full. So these are some of the commercial solutions available online. But as I said before, the main requirement for me was not to touch the water at all. So absolutely no contact. So now if I go back to my solution, you can see there are, like on the water tank, there are 3 sensors attached here. These are non-contact sensors that I'll be showing you in a while. These are quite popular nowadays. These are industrial level sensors which are very durable as well. They're waterproof and they are heat resistant, so they are ideal for fitting over your water tank on the external side. They don't touch the water, um, and I'll show how that works later on. So the first thing is these sensors are around 1.5 meter in length, the connectors at maximum. So what I had to do was I had to cut them halfway and then connect them to a Cat6 cable. That is your regular Ethernet cable. So if you remember now, the Ethernet cable has around 4 twisted pairs. That is a total of 8 wires. And each of these sensors actually has 4 wires. Like we have VCC, we have ground, we have level controller, high-low, digital high-low controller, and the output. And of course, I'll be showing you the sensors in details later on. So now, since each sensor has 4 wires, I take one Cat6 cable, and if I tear it open halfway, I have 8 wires coming out. So I connect 4 wires to one sensor and another 4 wires to another sensor. That means a total of 8 wires for a total of 2 sensors. And similarly, I had to use a total of 2 different Cat6 cables of 30 meter each for my use case. And when you connect these, you have around 4 sensors attached to the water tank. So in the diagram here, you can see there are 3 sensors, right? And the other one is actually on the pipe through which the water gets filled into the tank. Okay, that's a special requirement, something that I'm experimenting with. It helps you understand when the water is flowing through the pipe, so you can understand when the tank is when the pump is actually running. You can detect that. So now here in this diagram we have 3 sensors, but in our apartment terrace we have 4 sensors. Okay, now one is for the pump input, inlet, and then we have top, we have mid, we have low, and 4 sensors taken through 2 Cat6 cables entering my house in the 4th floor apartment. connected to my Arduino microcontroller system. Again, I'll be showing you the details of the microcontroller a little while later. So the input goes into Arduino and the calculation happens there, detecting the water level, changes in water level, etc. And then the output goes from the Arduino to the ground floor. That is again through one single Cat6 cable, that is 8 wires. So I'm utilizing 7 out of 8 wires, and we'll see how. We'll take a look at the indicator as well. And then on the indicator side, we have some LEDs, simple LEDs, and a buzzer alarm, which helps the security guard understand the level of water in the water tank, as well as whenever it's gonna reach the overflow condition, the buzzer goes, sounds. So that is how the system works and prevents water overflows. And in the other condition, when the water level goes down to low level, that is the last, this sensor, the lower one, automatically you can have the warning LED blinking on the ground floor, so the security guard knows that he needs to run the pump additionally for maybe another half an hour or 1 hour for the sake of emergency. Here I am on the terrace of my apartment where the water tanks have been installed, and here I'm going to walk you through the physical setup of the sensors. We'll see how the sensors are attached to the PVC water tanks, how the cabling has been done, and how the signal is carried over from here to the 4th floor of my house using Cat6 cables. So here we can see we have 4 different water tanks here, and all of them are connected serially through a joint in the lower section. So essentially all of these tanks are connected in serial, so they have a single capacity. And now this tank here, this is the primary tank, and when the pump runs, the water starts filling into this tank first, and then it goes into the other tanks that are connected. So let's call this the primary tank, and that's why I decided to install the sensors on the primary tank itself. So I'll be showing you the sensors separately, but let's see how they are installed first of all. So here we use something called, in India we call it putty. You can call it China clay or something like that. Because these are water sources, I didn't want to use something stronger that would cause permanent bonding, so I've tried to use this clay, so that if I need to change the sensor or if I need to make a repair, I can easily pull it out and add the sensors and put the putty again. So these are basically these clays are found on glassware shops, plumbing shops. You can get some of these and mix it with some olive oil and create a sort of a paste and apply that. It holds quite well, is able to go through both summer and winter, but eventually on around 7 months or so you need to change the clay again. So here is the first sensor, this one, okay, and it is connected, it's touching the PVC pipe directly through which the water comes in. So whenever the water flows through it, the sensor detects liquid and it sends a signal indicating that the pump is now running. Coming down, here we have the top level sensor. Once again we have the same clay here, and you'll notice I use the small plastic container. You can use this as a from any small box that you use in your kitchen, maybe for storing stuff. And what this essentially does is it gives a additional protection to the sensor inside. Let me take it a bit close. You can see the sensor over there. So I have added this insulation layer within the plastic container, and then have attached it there and sealed it with clay. This will provide additional protection from heat and rain as well. Now going down, this is the mid-level sensor indicating 50% water level, and this here is the low level sensor indicating 10% of water level. If I'm correct, this might be on right now. Yeah, you can see the sensor is on because the water is above this level right now, and I believe you'll see the same thing for the mid level, because currently the water level is more than 50%. So both of these sensors are sending a signal down to the microcontroller. Try to hold it steady so that you can see. Yeah. So now, as I said before, this here is a Cat6 cable. Okay, so I split the 8 wires into 4 wires connecting to this sensor, 4 wires connecting to this sensor, and similarly here we have another Cat6. This is getting divided between this sensor, the 50% mark, and the 10% mark here. Okay, and then you can see these wires go from here, 2 wires, 2 Cat6 wires carrying signal from 4 different sensors, and this goes down to my house. Now that we have seen how the non-contact sensors are attached to the PVC tanks, that's all about the installation. Now let's head down and take a look at how the Cat6 cable connects to the Arduino microcontroller and the different components that are used in building the unit, and what sort of calculations go on and what signal is sent down to the indicator down below. So here we are in my workshop room, as I like to call it, and this is where the microcontroller is located. The Cat6 cables come in through a opening in the wall, and they enter this room, and this is where they are connected to the Arduino microcontroller. So for an overview, this is a typical electric casing that I have used to construct the box for this setup. There are 2 exhaust fans over here to help remove any additional heat that builds up inside the box, especially in case of summers. And this is the router which helps connect Arduino to the internet, and these are just separate power supplies. This one for the microcontroller, this is specifically for the fans, and this is of course for the D-Link router. So this is where I'm powering the microcontroller with USB in this case, so that's like what, 600 milliamperes. And this is the internet connector, RJ45, that connects through a Ethernet adapter for Arduino, that is your W5100. And this is where another RJ45 cable is used to link up the output to the LED indicator located in the ground floor. So let me take a while to open this up and show you how things are connected. So this is the opened up enclosure, and you can see the microcontroller with its components laid out in here. Looks a bit messy, I know. So I'll go over each component over here one by one and explain to you how it works. So let's start with this. This is the connector section. This is where the Cat6 cable from the terrace comes in to the microcontroller enclosure and makes a connection right here. So on this side we have 8 connections, if you can see. So we host 2 sensors on this side and 2 sensors on this side. The top and the high level sensor, the top in the sense the pump level, the pump pipe sensor, and the 100% mark high level sensor are both connected here, and the mid and low sensors connect here. In terms of connection, this is the ground, this is VCC, this controls output level, and this receives the output. In this case, on the side, ground, VCC, output level, and output. Now these these sensors basically send out binary high and low. So using that, we need to calculate the current location, or rather approximate location of water level, as well as whether water is increasing or decreasing. So this raw data is fed into the microcontroller where all the calculation is done. For the microcontroller, I am using a Arduino Mega unit, and that is attached with a Ethernet module. This is called W5100. It helps you connect your Arduino Uno or Mega to the internet. Down here I have a temperature sensor. This is used for measuring the temperature inside the enclosure whenever the enclosure is closed. So it helps me keep a constant track on the state of things within the enclosure. Next to the microcontroller, on this side we have a RTC unit, real-time clock, and I'm using DS3231 with a rechargeable LIR 2032 cell. The clock helps the microcontroller keep track of time. That is used for internal logic whenever it has to match up with the pump running schedules. And next to the RTC we have a buzzer. This is an internal buzzer. It is used as a diagnosis buzzer, and whenever this microcontroller periodically keeps checking for operational failures within the system, if it detects anything that is not working properly, then the buzzer goes off, and wherever I am in the house I can hear it. It's quite a loud buzzer. So after the data is collected from the connection and fed into the microcontroller pins, and the calculation is done. So based on the calculation, output signal goes. You can see here we have a couple of wires going here. So each of these wires controls a LED in the indicator connected downstairs. So for high, mid, low, pump running, pump off, or system level, this depending on whether the system is working properly or not, we have a total of 5 LEDs connected to the indicator and a buzzer. So these wires control the LEDs in the indicator. And this little unit here is a voltage booster, which is used to boost 5 volt signal to 12 volt, and that is fed into the buzzer in the indicator downstairs whenever an overflow alarm has to be triggered. So each of these wires again connects to a standard RJ45 connector, because I am using 7 wires here, including the ground. So I can use a Cat6 cable. It has 8 wires, so leaving one out, I can efficiently make use of one single Cat6 cable going down from the 4th floor to the ground floor. The Ethernet unit here collects the data and after the calculation is done by the microcontroller, the data is dispatched using this unit to an online PHP server, where a program generates a human readable message, and that message is dispatched through the Telegram API and is delivered to my smartphone. So that is how I keep track of things happening inside the water tank, the level changing, pump running, and all that by just using my smartphone. So that's all about the microcontroller layout over here. We won't be going into the depth of the coding. Next, I'll be showing you the sensor itself, the sensor that we have deployed on the water tanks, and then we'll take a look at the indicator that is installed in the ground floor and see how that works, and then we'll see how the whole system works together. So here I have in front of me the sensor that I'm using for non-contact liquid measurement, and this sensor actually comes in two different variants. One is the circular type and another is the rectangular type. If you need to search for the sensor online, you would be searching for this model number XKCY25. These sensors have a voltage tolerance range of 5 volts to 24 volts, and since most microcontrollers like Arduino Mega work on 5 volts, this is ideal. If you try to use these with Node MCU, then you might need a logic level shifter. Now, the use of circular versus rectangular actually depends on the surface on which this is going to sit. For example, if you have a flatter surface, you would use the circular one, get good reading. And if you are putting it on something like a pipe or a curvature surface, then it is good to use this, because as you can see, when you attach this on a pipe along the long side, you'll get a better reading because most of the points will come in contact. And this sensor here comes with a assister that helps you attach this to the pipe. Okay, it's kind of like a band or something. Okay, so I'm not going to talk about this right now because I've been using the circular one in my projects, and I'll just open this and I will show you the different connection points. So this is what the sensor looks like. On this side we have 4 connector points. If you're trying to see here, you'll see there's a brown wire, a yellow wire, a blue wire, and a black wire. So the brown one is for VCC, so that should connect to your VCC. The blue one is for ground. The black one is for signal level, output level, and the yellow one is for output. So just to make you understand what is the output level, when you send in a binary high like 5 volts, let us say, and the area on which this sensor is attached has liquid on the other side, then on the output line you get a 5 volts. Okay, so you send a 5 volts, your VCC is 5 volt and output level is 5 volts, then you will receive 5 volts on the output if there is liquid at that point. If you want to receive reverse, that is 0, then you send a binary low on the output level. That will make sure that when there is liquid, it will give you an output of 0, otherwise 1. In most cases, providing a digital high on the output level is a standard process. There is one more thing about this sensor, that is you can actually open this here, okay, and you can see there's a potentiometer over here. You can take a fine screwdriver or something, connect it to the surface on which you're going to measure, and make some adjustments here that basically adjust the sensitivity. So for example, let us say I'm going to measure aquarium water level and I have thick glasses, then I need to make this sensor more sensitive, and for that I need to make adjustments to the potentiometer. And if you have a thinner glass which kind of gathers moisture, let us say in the area where there's no liquid actually, a good use case is maybe you're keeping hot water in a glass tank, so you don't want the sensor to capture the moisture, you want it to capture only the actual water level. So in that case you have to decrease the sensitivity, okay. So that's pretty much how these sensors work. And after this we'll be taking a look at how the indicators have been set up in the ground floor. So one more thing that you can take note of is that these sensors have these LEDs. So whenever they have an affirmation signal, like when you provide 5 volts on the output line and you get a 5 volts back, that means this light will be lit. So this is also a very good way to determine whether water is there at that point or not. How these sensors work, what is the mathematics, physics behind that, you can look it up on internet. Search by the name of the sensor, XKC. These are normally called induction sensors. So if you want to know how this works, you can look up how do induction sensors work, and you can get a lot of matter on that. So that will be all for this part, and we'll continue when we get to the indicator point. So here we are on the ground floor of the apartment. The cars are parked, and here this room is mainly for electrical equipments. It has the meters and fuse and all that, and this is where our indicator is attached. This is a Cat6 cable which carries the signal from my 4th floor room to the indicator. And here you can see there are 3 LEDs. This is low, mid, high. This is for greater than equal to 10%, greater than equal to 50%, and this is greater than equal to 100%. This is the system LED which turns on when you reset the Arduino unit, and this is the pump indicator which tells you that the pump is running right now. Here we have a few small holes for the sound to come out. Behind us we have the buzzer. The buzzer is triggered by the 12-volt power supply from the microcontroller, and it gives a loud siren sort of alarm sound down here. So this is also connected to a RJ45 connector. If you need to repair this or something, just have to take out the connector and take this upstairs and repair it and bring it back. So that's all about the indicator, and let's go upstairs and let's understand how the whole system works together. Now that we have seen how the system works, how the components are laid out, how the connections are made, now let me give you a final overview of the entire system as a whole to help you understand the entire functioning, and I'll also show you how the telegram messages are delivered to the smartphone. So here on my screen you can see there's a water tank block which represents a single water tank or a collection of multiple water tanks connected serially, and the water tank block is connected with 4 different non-contact liquid level sensors. The top one is the pump sensor, which is connected on the top of the water inlet pipe. The second is the high sensor, which is at the 100% mark. The second is the mid sensor, which is at a 50% mark, and the last one is the low sensor, which is on a 10% mark. Now each of these sensors give out a digital high or a low signal, and the Arduino operates them on 5 volts. So a digital high is like a 5 volt and digital low is 0. Now taking the signal from all the 4 different sensors, the Arduino microcontroller calculates the current state of water level in real time. So let us take an example where the low level sensor gives out a digital high and all other sensors are at a digital low. So from this we can interpret that the water level is currently at 10% or more, or rather you can say it's between 10 and 50%. Now again, if the mid sensor and the low sensor both are turned to a digital high and other sensors are at a digital low, so we can say the water level is at 50% or greater. In such a circumstance, if the pump sensor switches to digital high, we say that the pump started, and eventually as the water fills into the tank and suddenly the high sensor switches from digital low to a digital high, then we can interpret that the water level has now risen to 100%. Now when this happens, the buzzer and the indicator installed on the ground floor goes off, prompting the pump operator to turn the pump off to avoid overflow. And when that happens, the pump sensor will switch back to a digital low, indicating that the pump has stopped. And once people start consuming the water from the water tank, eventually the water level will go below the 100% mark and the high sensor will switch from digital high to digital low. So this is just an example of how the calculation is done within Arduino. And once the calculation is done, the data is dispatched into separate destinations. One is the indicator is controlled using that data directly from Arduino. On the indicator, the appropriate LEDs light up. So for example, if only the low sensor is on, only the low sensor is at a digital high, then only the first LED on the indicator, the first red LED is on. If the low and mid sensors are on a digital high, then the first 2 LEDs are turned on, and so on. The green LED turns on whenever the pump level sensor sends a digital high, and it turns off when the pump sensor sends a digital low. The yellow LED comes on whenever the Arduino microcontroller is restarted or reset. The microcontroller takes a certain bit of time. There's a delay in the code to initialize the Ethernet module, etc. So once that is done and all the sensors have been tested, the yellow indicator automatically disappears. On the other side, the interpreted data is also sent to a PHP web server, and the PHP script sitting on the web server takes the raw data, evaluates and generates human readable messages such as pump started, pump stopped, water level dropped below 50%, water level risen above 100%, like that. So this data is then sent to smartphones using a Telegram API. So instead of developing a custom app, I'm leveraging the Telegram API. So people who need to receive the notification will have Telegram application installed on their smartphones, and they would have joined the Telegram channel that I've created. The PHP web server acts as a Telegram bot. It uses the bot API keys to send those messages into the channel, which is subsequently received by all the different clients who are connected to that channel. So in the meantime, let me also show you what the messages look like. So I'm going to switch to the web version of Telegram, and here we have two things. This is the public channel on which message notification is sent to all the different people who are subscribed to this channel. So here you can see we have messages like pump stopped, pump started, water level risen to 100%, and all that with the proper timestamps. So you can see how utilizing a well-developed platform like Telegram saves you a lot of development effort here. And then there's another channel here. This is not a channel, it's a private chat between me and the bot. So these are messages that are sent by the bot to me only, and these are debug level verbose messages, so they can help me track down bugs in the system, and they help me monitor the system more efficiently. So here you can see we have a message field, we have pump state, not running or running, then we have system temperature, which is taken from the temperature sensor installed inside the enclosure. We have system health, which is derived from testing all of the sensors. Then we have the sensor values, P equal to 0, P is the pump sensor, H is high, M is mid, L is low. So these values can be 1 or 0. So these are the raw values. Then we have RTC time, which is taken from the RTC unit, DS3231. Then we have the server time, which is coming from the PHP server. And having both of these side by side helps me understand the total delay between when the message is dispatched from Arduino and when it is received on the smartphone. And finally, we have a field called runtime, which is like a day counter. It counts how many days Arduino has been running for. And this is also very helpful when there are some memory leaks and all. You can understand how many days the system has been running for before the problem occurs. So this is basically how messages are received by people who have Telegram application installed. So that's about it. I hope this was helpful to you and it will inspire you in creating something of your own. And if you have questions, you can leave it in the comment section below. And if you create something, also share it with me through the comment section below. And that's all for me. See you next time with another interesting topic. Signing off. This is Rajdeep Rath. Thank you.